So in the last couple of classes, we saw Huffman coding and Shannon coding and some bounds on the expected length. We know that Huffman codes are optimal. We proved that in the last class. So they achieve the minimum expected length among all possible prefix-free codes. Right? And we saw a few handwritten examples where we found the Huffman code for a given distribution. In today's class, we'll try to write a program to design the Huffman code for any given distribution, and if time permits, also see how it works on a sample text file. All right. So to understand that, let's try to work out a simple example by hand to see what are the main components that we need to design a Huffman code. Right. So let's take an example distribution of 1/4, 1/8, 1/8. So the Huffman coding procedure works by merging two symbols, the two least probability symbols in every step, right? So in the first step, we would merge these two. Let's suppose that I have four symbols, A, B, C, and D with these probabilities. I would merge the two least probability symbols, in this case C and D, to get this super symbol CD. In the next step, I would again find the two least probability super symbols, so in this case I have A, B, C, D. C, D, and B are the two least probability super symbols. I merge them to get B, C, D, and I'm left with two super symbols, A and B, C, D. I would merge these two to get A, B, C, D, right? That's how the Huffman coding procedure works. That's the way of generating the Huffman tree, right? So if I want to write a program to design the Huffman code for a given distribution, what I need to do is at every step, I need to maintain a list of existing super symbols, right? In this case, originally the set of super symbols were A, B, C, D. In the next, I had A, B, and one super symbol CD. And the third step, I had two super symbols. And finally, I have only one super symbol that is left. All right. So how can I represent a particular symbol? I could represent this as a node in a tree. So if you think of this tree, which is sort of lying horizontally, this would be the root of the tree, and they would have children. So this root has two children, A and B, C, D, and B, C, D has two children, B and C, D, and the C, D has two children, C and D. Right? That's one way of looking at this particular Huffman tree. Right? So this would give me the code tree. So the most fundamental element of this code tree is a node. Right? So I need some kind of a data structure to represent a node. What does a node consist of? A node consists of labels, right? So the label for this particular node is ABCD, the label for this node is BCD, for this node is A, and so on, right? So a node has a label, and for every node there is an associated probability, right? The probability of that particular super symbol. And potentially a node may have one or more children, and perhaps a parent, right? So in this case, ABCD has two children, A and BCD, but A doesn't have any children. Right? So the first step is to define a data structure for a node, and we'll do that first. So does how many of you have already seen some amount of object-oriented programming? How many of you have not seen any object-oriented programming before? You don't know what a class is, nothing. Right? It's okay if you don't know, then just think of this as an implementation of a custom data structure. That's it, right? It'll be fairly intuitive. We will not use any sophisticated concepts except how I define this particular data structure, nothing else. Right? So I'm defining a custom data structure called a node. And every time I instantiate a realization of this particular node, this function is going to run. Okay? And for this node, I'll define certain variables. The four fundamental parameters of any node are going to be the label of the node, the probability associated with that particular node, the label of or what the left child is and the right child is. So it has potentially two children, and I'll call them the left child and the right child. Right? So initially, when I instantiate a node, there won't be any children. Right? If I want, I can add children later on. Just to see this working, let's create a custom node. Say node 1 is node, and when I instantiate this, I need to specify what the label of the node is and the probability corresponding to the node is. Don't worry about what the syntax is, what this init means or what self means and so on for now. So let's say I want to create a node with node label A and probability being say 0.5. Right? So this has created a node. If I want to access the label for this particular node, then I just say node 1 dot label. If I want to access the probability corresponding to that node, it's node 1 dot prob, right? This particular variable here. So this node has label A, probability 0.5, and no left or right children. Now to add a left and a right child, let me create two more nodes. And let's say that I set node 2 to be the left child of node 1 and node 3 to be the right child of node 1. Node 3, and let me print so the left child is or the label and the probability are still the same. but we see the left child and the right child are not none anymore, but there are certain objects. So if I wanted to print the labels corresponding to the left child and the right child, I could just do node1 dot left child dot label. Those would be B and C. Okay. So that's all the object-oriented programming that you need to know, at least for this class. So now we have some way of manipulating nodes. How do you add children and so on? Okay. So in our Huffman coding, or in the process of designing the Huffman tree, the most basic operation that we need to perform is you merge two nodes together to form another node, right? So let's write a function to do that. And the way I'll define the label corresponding to the merged nodes is that this will be a concatenation of the labels of the two nodes. And what will be the probability of the merged nodes? Just the sum of the probabilities of the two individual nodes. So this returns the new node that is created. Let's see this work. So let's say that let me create a new node. Let's node 4. And I want to have node 4 being the concatenation or I want to get node 4 by merging, let's say, node 1 and node 2. Okay, I missed something here. So I merged these two nodes, but I also have to define the left child and the right child of these two nodes. Right, so this has, I've merged nodes 1 and 2, and the label for the merged node is AB, which is a concatenation of the two labels. The probability is the sum of the two probabilities. The left child is A, node A, and the right child is node B. All right. Any questions so far? Okay. So now let's try to have the Huffman coding procedure. Okay. So first, we need a particular alphabet to work with, and we also need a probability distribution. So let's say that the alphabet is A, B, C, D, and E. So it's an alphabet of size 5, and the probability mass function is, I don't know, let's say it's some sequence of decreasing probabilities. Some probability mass function, right? The probabilities are 0.43, 0.21, 0.14, 0.10, and 0.08. So to create the Huffman tree, I need to know what the alphabet is and what the probability mass function is. And let's go back to this example to understand what exactly we need to do to think about the logic to write this particular part of the code. At each step, I need to have a list of the nodes available to me at this point, right? So initially, the nodes available to me are one node for each symbol. And later on, at each step, I need to merge nodes together. When I merge two nodes together, I have to remove the nodes that I had merged and replace that with the merged node. Right? So first, let's create one node for each symbol. So for each symbol in the alphabet, I have to create a node. Let's say that this is the list of nodes that I'm going to maintain at each step. So I create a new node, and the node is going to be, it's going to have the symbol being the ith symbol in the alphabet, and the probability is the probability corresponding to that symbol. So at the end of this step, I should have the list of nodes. Right? Just test this out. Right? So it's creating one node for each symbol in the alphabet. Okay, once we create this, we now need to go through the procedure of merging nodes together, right? Until all of the nodes have been merged together, right? So when does the Huffman merging process stop? It stops when there's only one node left. So as long as the length of this list of nodes is greater than 1, you keep doing the for while. All right. So now what do I need to do? I have to sort, right? I have to sort all of the symbols in increasing order of probability. So I'll sort right. So I get the sorted array. Let's say node 1 is the smallest symbol, or the symbol with the smallest probability, and node 2, sorry, sort So these are the indices of the symbols with the two least probabilities. And I now have to merge nodes together. Nodes. So this is the merge. What next? What do I have to do now? Yeah? Yes? Correct. So I have to delete the nodes that I have merged and then add this merged node to the list. Right? At the end of each step, let's also print the labels of the nodes that are still present. At the end, we'll just return the root node, right? So originally, remember that A, B, C, D, E are symbols in decreasing order of probability. So ideally, we should be merging DE and then CDE and then BCDE and A. That's how it should ideally proceed. Depends. I think in this example, that's how it should work. All right. So the first step is it merged nodes E and D, and so there were four nodes left over: A, B, C, and ED. And the next step was you merged nodes C and ED. So you got A, B, C, E, D. Why was this? Nodes. So for some reason, C was not merged. I'm sorry?
Can we remove first remove and one append instead of
We could. I'm not sure why that should make it. Okay. I think that's the problem. Yeah, this should be fine. I think this is a better way of doing things. I think this will work. I should probably. It's because I'm sequentially deleting these. So I have node 1, node 2. Okay, so first step was you merged D and E to create the symbol ED. Uh, the next was the two least probability symbols now were C and ED with probabilities 0.14 and 0.19. So you merge these two to get CED, and the probabilities are zero point 0.2 and 0.34. The two least probability symbols are B and CED, and you merge these two to get BCED. Uh, and then finally you merge everything together to get ABCED. Right? Great. So now we have a function that, given any probability distribution, this creates the Huffman tree. Okay. Okay, so now we've created the Huffman tree. We now need a way to find the code words for any particular symbol. So we have this tree which I can access by starting traversing from the root, and then I can go along any edge. Okay. So to find the code word, I have to start with the root and then keep going until the leaf that I'm looking for is the symbol which I want to encode. So let's do this. Let's try to find the let's write a function to find the encoding of any particular symbol. So I need to specify the root node as a parameter for this function and the symbol that I want to encode. All right. I'll represent the code word as a string of zeros and ones starting from the root. So what do I need to do at each step? Let's again revisit this example. I'll start from the root node, right? Let's say I want to encode the symbol B. Okay. I start with the root node, and then I look at the labels of the two children, the left child and the right child. Now, if the label contains the symbol that I want to encode, if the label contains B, then I go to that particular node. So I start with the root node. I look at the left child. In this case, it is A. Of course, here it's not left child. By left child, I mean the one that is at the top, and the right child is the one that is at the bottom. So the left child, I look at the label. Does it have B? It doesn't. I look at the right child. Does it have B? Yes. The label does have B. So I now move to the right child. That's going to be my current. And if I move to the left child, then the label corresponding to the edge, let's say that this will be equal to 0. And if I go to the right child, the label is going to be 1. Now this is going to be my current node. Now from the current node, I again look at the two children. The label of the left child, does it contain B? In this case it does. So I move to the left child and the label is going to be 0. And at this point I stop, right? Because I've reached the leaf, and the way of checking whether I've reached a particular leaf or not, how do you check whether some node is a leaf? It should have no children, right? Both the left child and the right child should be null. So now what do I have to do? I have the symbol S. I want to check whether the symbol S is present in the label of the left child or the right child, right? If the symbol is present in the current node, in the left child's label, what do I do? I first append symbol 0, bit 0 to the code word, and then what should I do next? Now I need to move the current node to the left child. Otherwise, right? And in the end, okay, let's test this out. So for this example, the code word for A happened to be 0. For B, it is 10, C 110, 111, and for D, it is 110. Right? Just a sanity check, this forms a prefix-free code. Okay. Questions? Okay. Now let's say that I have, okay. Now that we've designed the encoder, we also need to design a decoder. So the encoding process was you start from the root and you keep traversing down the edges until you reach a leaf, correct? And then read off the symbols along the edges. The process for decoding is similar, except that you don't check the labels of the nodes, but rather you check the node edges, sorry, the edge labels. So if the next bit that you read is a 0, then you move to the left child. If the next node that you read, if the next bit that you read is a 1, then you move to the right child. We'll generalize this sort of one step further. We'll assume that what we receive is not necessarily just a code word, but can potentially also be a concatenation of code words. Right? So even if what I see is an arbitrary string, it can be of arbitrary length. If If it's a concatenation of code words, it should still output the sequence of symbols that correspond to that concatenation of code words. Okay, so for this, what do I need to do? I again initialize the current node to be the root node. So let's say that L is the number of code word bits or bits of the received string that I have processed so far. All right, so that's the pointer to the current bit that we are processing. In fact, I can probably just string. So if this is equal to okay. So if the next bit that I read is equal to the 0 bit, then I need to go to the left child. If it's equal to 1, I move to the right child. And now once I go to either the left child or the right child, I now need to check whether this is a leaf or not. If it is a leaf, then it means I am at a position where I can decode a particular symbol. And I can output that decoded symbol. And now I need to again reinitialize the current node to the root node. So I output the label of the leaf node that I'm at, and then initialize the re-initialize to the root. Okay, let's see whether this works. Say that what I want to do is find the code word, which is this. Okay, so I've encoded A, B, C, D, and E separately, and they're all decoded correctly. Okay, let's also test this with some examples, some example string. Say A, B, C, C. In fact, let's do the following. So we have a probability distribution. Let's generate a random sequence of symbols drawn from that probability distribution. So to do that, let's say I have 5 symbols for now, and choice, alphabet. I need to generate n symbols and with probability equal to p. The random string would be right. So this generated a sequence of 5 random symbols. Every time I call this, I get a different sequence of symbols. Right? Uh, Seems a bit weird because A is supposed to have the highest probability, but you don't see as many A's. But whatever. But anyway, I think the probabilities are not too different. Okay, now we need to generate the encoded string from this particular random string. In random string, you just append the Huffman encoding of the next symbol. Right, so this happens to be the encoded string. So I took 5 symbols, I encoded all of the symbols and concatenated the encodings of all the 5 symbols. Now, if I just look at the string, there's no way I can say where the encoding of the first symbol ends and where the encoding of the second symbol begins, right? So let's try to decode this. Yes.
Could you explain decoding Huffman?
Okay. You mean this particular function? Okay. So how should the Huffman decoding procedure work? Let's take maybe this example itself. So A, B, C, D, E, I have 5 symbols. The Huffman tree would look something like this. I have the root node, which is A, B, C, D, E. I have this node has two children, A and B, C, D, E. The node B, C, D, E has two children, B and C, D, E. This has two children, C and D, E. And this has two children, E and D, I think. Yeah. The edge labels are 0, 1, 0, 1, 0, 1, 0. I'm sorry? I think in this example, the left side, yeah, the left side is E. I mean, that's how this encoding. So the main thing is both of them are valid Huffman codes. You can tweak the code to make sure that, for example, you also take care of the ordering of the symbols, but we have not done that here. Okay. So now let's say I see an example string like this. So 0, 1, 0, 1, 1, 0, 1. Right? 0, 1, 0, 1, 1, 0, 1. And so on. What should it do? It reads the first, so it starts from the root, that's the current node, right? I read the first bit of the received sequence. It is 0, so I move to the left branch, go to the left side. All right. So initially I initialize the current node to the root node, and I read the received bits in sequential order. For the current bit, if the current bit is equal to 0, then I set the current node to be the left child. Otherwise, I set it to the right child. And this is done at every step, right? So up to this point, it should be okay, right? Next, let's take this particular example. I started with the root node. The first bit was equal to 0, and I moved to the left child. Now this node doesn't have any children, right? Which means that at this point I can decode. I've already reached the leaf, and the leaf node is labeled A. So then I can output A and then move to the next code word bit. But in addition, I also have to set the current node to the root node. I have to reinitialize. And that's exactly what is being done here. How do I check for a leaf? If the left child is empty and the right child is also empty, then it's a leaf. So then I can output the label of the current node and then reset the node to the. Which one? The current node value is A. Right. Is that okay? Any other questions? Great. Okay, so now I've taken a random string. I have generated the encoding of this particular random string, and now I wish to decode this. It happens to be the same, right? Let's test this for a slightly longer string. Let's say 1,000. Maybe, yeah, let's take 1,000. So it's a long sequence of symbols. And let's encode this, again, some very long string. And I can't manually verify, so let's say I do the following. So it's decoded this very long string correctly. But okay, let's now also see what is the length of the compressed string, or what is the rate. Which is equal to the length of the encoded string divided by the length of the random string, which is n. But in addition, let's also compute the entropy of the true distribution, right? The Huffman code is guaranteed to be within 1 bit of the true distribution. So the entropy should be the sum of pi log 1 over pi yes.
So encoded string is basically a binary string.
The encoded string is a binary string, yes.
But the random string, which is basically alphabet, which
Correct.
is actually represented in the form of ASCII characters, which each one is 8 bits long.
Okay.
Is the formula for
Right now we are assuming that the alphabet is A, B, C, D, E. There are only 5 symbols in the alphabet. Okay, that's the assumption that we will run with. So if I had to represent it in raw form, because we've assumed that the alphabet just contains 5 characters, if I had to represent it in the raw form, I would need log of 5 to base 2 number of bits to represent this, or ceil of log 5 to base 2 number of bits to represent in the raw form. But in the compressed form, that's going to be even less. Let's is this any no, right? The rate of the compression should be less than or equal to log cardinality of x. So the question is, how do you compute the rate, right? If the rate is the size of the raw file, sorry, the size of the compressed file divided by the size of the raw file, when both are measured in bytes, then that should be less than 1. But here I'm measuring the rate as the number of bits in the encoded string divided by the total number of symbols, which can be greater than 1 if the alphabet size is greater than 2. Right. Did I change the distribution? I'm sorry? It should be reasonably good even for n equal to 1000. So I think there is something very This is larger, but ideally even for n equal to 1,000, this should work reasonably well. In any case, the expected length should be greater than the entropy. Of course, ultimately it depends on the actual frequency of occurrence of the symbols. So let's try to find the frequencies. But sure why the actual distribution seems to be very different. Okay, I'm not sure. Something weird with np dot random dot choice. It's only picking us. Yeah. We can, but that shouldn't matter, right? Okay. I think this was a silly mistake that I made. This should just have been alphabet of I. Yeah, no, it's fine. Right, so the rate of the compressed string is 2.2. Now the symbols are actually generated according to the correct distribution, and the entropy is 2 point something 0 something bits. So it's between the entropy and entropy plus 1 bit, right? Okay, so let's we still have about 10 minutes left, so let's see if we can do a little bit of string processing. So right now I have a text file. Well, just take this text file and paste. It's a huge file, and let's say that let's say I only want to read lowercase letters. I just eliminate everything else from the string. All right. Great. So what I've basically done here is I just read a text file and I only retained lowercase characters. I threw away all of the other characters in the text. Right? All other characters, including uppercase as well as punctuation marks, spaces, everything else. So I ended up with a string of this particular length. So it's whatever 69,765. And this is the frequency of occurrence of various characters in this particular text. All right. So let's now, given this, we can try to compress. We can also try to find the entropy. Let's say that P is equal to I need to convert this dictionary to an array. So this is basically the distribution of various characters. Okay, let's create the Huffman tree. The alphabet is a list. So it's now created the Huffman tree. Let's go ahead and encode. Once I have the encoded string, let's decode. Right, so this was decoded, encoded, and decoded correctly. Let's look at the length of the compressed string. So the rate is the length of the encoded string by the length of the random string, and the entropy is right. So in this case, the entropy turns out to be 4.16 bits. Let's also, for reference, see what log cardinality of the alphabet is. So the entropy is not too low in this case, right? In fact, log cardinality of x is 5. The entropy is 4.16 bits, and the rate is pretty close to entropy already. It's 4.19 bits. Right? So Huffman coding is good, but in fact, if you try to use a standard text compressor like zip, it will give you a much better compression rate than what Huffman codes can give you. And the reason why these text compressors like zip are so much better is because right now what we've done is we've encoded it symbol wise, and that automatically puts a bottleneck. You're not making use of the dependencies among the characters. You can view the random string that you see as a Markov chain in the case of English text. And absolutely, so this joint distribution of the symbols is never made use of when you do symbol-wise encoding. So Huffman coding is nice, but it is strictly suboptimal. Right? So in the next step, what we'll see is, in future classes, we'll see how you can make use of this dependency. If you're given a Markov chain, then how do you encode it? How do you compress it to get down not just to the entropy, but the entropy rate, which can be strictly less than entropy. Right? Okay, so let's stop here.